Good morning, everyone. Uh, so, hope you all had a good weekend. I hope it wasn't too disturbed. Good morning, Sam. Too disturbed by the fact that I promised you that I would tell you why continuous functions, why these continuous functions are not differentiable, uh, and then you were left to be left in suspense for all the weekend. Um, Although you do have a book that has all the spoilers. So probably you were sleeping fine. So, um, like I promised, differentiable functions are continuous. So, this is so this is the theorem. The theorem is that any differentiable function is continuous, and it's not even that complicated. Basically, you look at the limit and you think, how could this limit exist if the function is not continuous? And the answer is that it couldn't. So, let's see. Suppose a function is differentiable at so basically this is how it goes. If the function if a function is differentiable, um, that's the same as saying that the derivative exists, that this limit exists. So low system resources may affect your audio quality. Try closing some applications to improve performance. Well, I can close. Should I close Zoom or should I close? Um, if only you would let me close all the software that I didn't want. Should I close the antivirus? Can you hear me? Is it that you can't hear me, or is it that you can hear me? Okay, it's just that you can't hear the whole extent of the beauty of my voice. I'm fine with that.
Sounds pretty good to me right now.
Okay, well then it's just I think Zoom got updated, so maybe this is the same audio, but a new message because the enter exit chime is no longer called. It's called a sound when participants enter. Okay, well I'll keep going then. All right. So how could this limit exist? Well, the thing is, this is a fraction. The denominator goes to zero. So um, this limit is something divided by zero. So um, if this limit has a chance to exist. So the thing is, if I have a number divided by 0, then the limit is not going to exist. It's going to be plus minus infinity. If I have something that doesn't exist divided by 0, then that's a good question. But I'm about to see that the limit has to be 0 divided by 0. Because when the limit is 0 divided by 0, then anything could happen. For example, it could exist. So what I can do, so I want to see if the limit, if this limit is 0. No, not that limit. And one thing I'm going to do, so I know a limit that exists. It's a derivative, so I can multiply and divide by the same thing. These two are the, if one exists, the other exists because I multiply by 1. But now, using the product law, the thing is, this thing, this limit exists and it equals f prime of a. So it equals a number. This limit exists. I know this limit, and it equals 0. So if I multiply a number by 0, I'm gonna get 0. And that tells me that the limit of f of x minus f of a is 0. This is another way of saying that the limit of f of x is f of a, if you like, by the sum law. Yeah. What's happening today? I feel like my internet is crap here. So the limit of the function is the value of the function. That is to say that f is continuous. Okay, so so that was the proof. Now we know for sure that we will never find a discontinuous function that is differentiable at a point where it's discontinuous. So about proofs in this class, I'm not gonna ask you. They're not the most important thing, but they're nice. The proofs that I am doing, because I'm skipping a lot of them, are a good practice of the things we already know. Like here, this was a little bit of algebra, a little bit of the limit laws. So I don't know. Maybe proofs have more letters than we like, that we're used to. But we should still try to understand them and maybe not panic if we don't. Are there any questions?
So you're trying to get rid of the denominator in order to make it exist at that certain point?
Well, the thing is here, so here it was very convenient for me to write this limit because that is the one limit I was told exists. I said if I start with a differential function, I know this limit exists. So I guess there was no denominator. I wasn't trying to get rid of it. I was trying to get it to be there, so that it would be convenient for me. So the thing is, why did I do that? Because I wanted to get to here where I could split this into two limits that I know. Does that make sense?
I mean, kind of. So is the limit like something over zero? Is like when you mention above the limit is question mark over zero, and so you're trying to multiply by the denominator in order to yeah, I don't know
So,
what
I
it
mean,
means.
this is not a thing that happens often. That you know what the answer to a limit is, but you don't know what the thing in there is. I guess it happens sometimes because it just happened. But this is a very kind of a different question from the usual question of what is the limit of this formula. You know, because here the thing is, I knew what the answer was. I kind of didn't know what the intermediate step was. Normally, if I'm computing a derivative, normally I'm trying to get the answer. But here I'm saying, imagine that I knew the answer. So I know what the answer to this limit is. I know what the answer to this limit is. Trying to figure out the answer for this part. So it was a different kind of question. I guess required a different kind of solution.
Okay, that makes sense.
Okay. Right. So the takeaway is that if a function is differentiable, it has to be continuous. If a function is not continuous, it has no chance of being differentiable. Does this mean that if a function is continuous, then it is differentiable? No, because I only made one promise. So um, so back to where I was on Friday. Um, here's some common ways in which functions are not differentiable. Uh, so so the answer basically I have three examples where this happened. We've seen all three. Um, if a function is discontinuous, then it is not differentiable at the point where it's discontinuous. So a function that looks like this, it cannot have a tangent there. A function that looks like that cannot have a tangent over there. A function that is not even defined cannot have a tangent. Um, a function that doesn't have a limit cannot have a tangent there. So how can you be discontinuous? You could have different left and right limits. You could have equal limits, but they not equal the value of the function. You could have limits that don't exist, like these two. Uh, and in none of these can you basically. I mean, to be differentiable, it really means that you zoom in and the curve looks like a line, and neither of these look like a line, no matter how much you zoom in. If I oh, there's a well, I can't really zoom in. There's a really big difference between zooming in here, where it eventually looks like a line because this function is differentiable, and here, no matter how much I zoom in, it doesn't look like a line. It might look like a line with a hole, but it doesn't look like a line. Uh, so another example that we saw on Friday is if they have things that look like corners, they are not differentiable. And again, the absolute value. So this one is continuous and still not differentiable. If you look in here and you zoom in, what does that corner look like when I zoom in? Well, basically exactly the same. Still looks like a corner. Can I keep zooming in and expect it to look like a straight line? No, it looks like a corner. And the last example, so these are continuous. And the last example is if you have a vertical tangent. Which would also be continuous. So an example we've already done is the square root. We did this computation, we saw the square root is, the derivative is 1 over 2 times the square root. This is a function that is not defined at 0. Even though there's a square root at 0, there's no derivative there. And not only that, but we can see that as x approaches 0, the derivative approaches infinity. So what is a line with slope infinity? It's vertical. I mean, as well, let's draw it. So this is the square root. It's a parabola. Doesn't look like a parabola very much. No, it looks more like a parabola. It's a half parabola. And the derivative looks like 1 over x, basically. Has an asymptote. So what's happening? Let's look at it. So what's happening is that as I approach 0, the slope. So here, notice that it looks straight. It's differentiable, but it gets. We're going more and more downhill, and so this means that the slope is getting bigger and bigger. Here, for example, the slope, as I go 1 to the right, I go like 4 up. The slope is probably something like 4 here. Then I keep going. The slope is probably more like, I don't know, 8 over here. And I keep going, and the slope keeps growing and growing, and eventually it gets vertical. And vertical, well, eventually it just looks like the axis. But here, I promise you, well, spotlight. What? You see my mouse? Yeah. So here, it's not completely vertical. It's never completely vertical until you get to exactly the origin, and at the origin it's vertical. And there, well, I would say it has a tangent. I would say a tangent is vertical, but the derivative cannot know that, because the derivative cannot. We can't write a function whose graph is a vertical line, because a vertical line is not the graph of a function. Doesn't. So in this case, there is a tangent line. It's this one, but the problem is that this is the line x equals 0, which doesn't look like y equals mx plus b at all. So vertical line have infinite slope, really. I mean, when you go 1 to the right, you you don't go up or down because you just can't go one to the right on a vertical line. And these are the the common examples. There you see of functions that don't have a tangent, functions that are not differentiable. The there are more. It's really not possible to classify. Like um, for example, so there are functions that look very weird that we're not gonna care. Um, but there are functions that really are continuous and they have no derivative anywhere. Like this stuff down here, it is continuous. This is the movement of something that moves randomly all the time. I think that I don't know much physics, but I think the first time this was studied was the movement of a grain of pollen in a glass of water. It the path it takes is just random, and not like at every second it changes randomly direction, but more like at every instant it changes direction randomly because a grain of pollen is so small that it's getting hit by water molecules so much. The water molecules are so big compared to it that at some moments more molecules are hitting from the left and from the right just randomly, and then if you're being hit by 5 molecules on this side and 3 molecules on this side, you move to this side, and but then the next instant something different happens. So in the end, the movement is completely random, and that turns into something that has no derivative, even though it's continuous. So continuous functions have no reason to have a derivative, but that said, our day-to-day functions that we see, especially the ones we see in calculus, do have a derivative. So I'm just not claiming that Brownham motion is not a part of this class, just claiming that this is not a complete list. It's a complete list of the common things you see. Okay, so there's one last topic in chapter 2, if there's no more questions, and that's the second derivative. So what's the second derivative? The second derivative is the derivative of the derivative. So basically you have a function and you know you can do a thing to it, which is to take the derivative and get another function. And then you get a function, and then you go, why not take another derivative? Why not keep going? Why not take a third derivative or fourth? The answer is you can. So so this is just what it is. We write it. Really, this is all there is to it. We can then think about what this means, but I already told you everything you need to know. So we write it, if the derivative we write with an apostrophe, the second derivative we write with 2. And what it just means is take the derivative and take the derivative of it. You can also, so this is just terrible, but if you write it in Leibniz notation, you write it like this, kind of, I don't know, I have no explanation for this. We do this crap because that's how it's always been done. We write the square on the D and on the as if dx was a thing that we were squaring, and as if d was a thing like that we were squaring, or as if d dx was a thing that we were squaring. You had to understand, people 300 years ago did math in a way that was basically, was, I don't know, in a lot of ways it was almost like poetry and not math or metaphysics. So we're like, take an infinitely small thing and square it, and then get a squarely infinitely small thing. They were all wearing tinfoil hats. So, so what does this mean? So, how can we look at a function and guess what its second derivative is? Because I feel like if we can look at a function and guess its second derivative, that means that would mean that we understand it pretty well. For example, so say that I have a function like this. So I know what the derivative is supposed to look like, or, well, I know, but this is a pretty complicated thing. It takes practice to learn how to do this. It tends to be very confusing at first, but it's definitely worth it to understand. So I would go, these points are pretty special because here the tangents are horizontal, and then to the left of this point, the tangents are going down. They have negative slope. Well, yeah, I'm already super laggy today. And here at this point, the slopes are so the slopes are zero. So the derivative, the graph, goes through these 3 points. Over here, it goes through. It's negative because the slopes are negative. The function are going down. Here, the slopes are going up. So up, down. So going up means positive derivative. It's a relation between going up and being positive or negative, and seeing that in a picture, I think that confuses people a lot. So negative, positive, and then we're going down, so we're negative again. Then we're going up, so we're positive again. So the derivative looks something like this. So what does the second derivative look like? Well, the second derivative, it looks like we do this process again to the function that I just got. So, for example, I got this new special point here that I wasn't looking at before, but at this point, the tangent of the derivative is horizontal. So there's going to be 2 points now where the second derivative is 0. And now to the left of this one, this function is going up. Goes up, then it goes down, then it goes up again. This means that here is going to be positive, then negative, then positive. So it's probably going to look something like this. So what is this telling me? So this is telling me something. I mean, I think just because I got it from f of x, there's going to be something that this is telling me about the function. So if I read this correctly, the fact, for example, that this is positive, that means so the rate of change of f prime of x as x changes. So that is what the derivative of f prime of x is. But now, what do I mean? What does x prime of x mean? X prime of x is the slope of f of x. So the second derivative is telling me how fast the slope of the original function is changing. So what I'm saying is that this function is going down. It's going down, but as I approach this point, it's going down, but it's getting less steep. So less steep means it's going, I guess, more up. And the fact that this is going more up is telling me that this function is positive here. Now, this function, for a little bit, it gets more and more steep. It changes, and then, well, it gets more and more steep until at some point it gets less and less steep. It's basically in which way the graph is bending. I mean, we call this curvature. So since this function is getting less steep, it's getting more steep down here. This is negative. This is what this is telling me about this part of the graph. And then finally, on this part of the graph, again, the function is bending up again. I guess for you it would look like this. And bending up means your slopes are getting bigger. If your slopes are getting bigger, your second derivative is positive. Let me do a legit drawing so you.
Wait, so we find like the first, so we find the first derivative to find like the slope of the function, and then like the second derivative is to see how fast that slope is changing.
Mm-hmm. I mean, I'm gonna show you. If you give it a couple of weeks, you'll see the most very important use of the second derivative, which is to make the most money. So take this function, which looks pretty similar to the one I drew. So this is the derivative, and this is the second derivative. Maybe. So, okay. So first, in red we have the function, and in blue we have the derivative. So you can see where the function decreases, the derivative is negative. When the function increases, the derivative is positive. But now if we look at the second derivative, let's ignore the first derivative. So this one, it's positive. So this is the, well, how do I draw this? This is the part where the second derivative is positive. Oh, that's great. So this bit here. And what happens from here, from this point to the left on the original function, is that first it's going down, then it's going less down, eventually it goes more up. So basically it's curved up. So the second derivative tells you how the function curves. If we look at the second chunk, so between these 2 points, these are the points where the second derivative is positive. So these are the parts where so first the function, it's going up, then it's going less and less up, and then it's pointing more down. All of these are a decrease in the slope. and finally it becomes positive again. Uh, oh, I meant negative here. Finally becomes positive again. So the original function starts to bend upwards. Here, I mean, here you can't really tell that this has bigger slope than that, but it does. Um, and that's the story of second derivatives, right? At least second derivatives and graphs. Are there any questions? So far, I guess this is useful for graphing. I don't haven't said anything else that it's useful for. For the second derivative, the slope increases. Well, if the second derivative is positive, the slope increases, because the second derivative being positive means the change in the slope is positive, so the slope is increasing. If the second derivative is negative, the the slope decreases because it means that the change in the first derivative is negative. So another way to think of the second derivative in a particular example is in the example of a moving thing. So, which so change you've already seen. I don't know what high school physics covers or whatever physics class you might be taking now. Um, in another example, if f of t, now I'm calling it t because I'm thinking it's time, is the distance traveled by a thing after t seconds. Then we've already talked about the derivative of distance, and that's velocity. uh, this is the change in distance over time. The change in distance, how much distance we move per second, which is say the velocity, and let's just call it this v of t. So what is the second derivative? The second derivative is the change in velocity now. What's that called? Maybe not all of you have seen it, but someone's gonna know. Autumn.
Acceleration.
Acceleration, yeah. Acceleration is how much your velocity is changing. Uh, if your acceleration is positive, means you're going faster. If your acceleration is negative, it means you're going slower. Acceleration is what um, makes you feel a force. If you're in a car, if you're in an elevator, for some reason in physics they love elevators. If you're in an elevator, you feel a little. It starts going up, and then you feel a little bit pushed down. Then it starts moving. Then it starts moving, and if it moves at a constant speed, then there's no change in velocity, and you don't feel the accelerator moving. I mean, if you do, it's in your imagination. But there's really no way for you to tell if an elevator is moving or not. But you feel exactly the same. And then at the end, it decelerates, it breaks, and then you feel a bit weightless because you get pushed up. So all right. So I guess for the last thing, let's do a contest. um, I have a ball, right? Do I have a ball? Okay, so you start a car. So you're stopped. You start a car. You accelerate to say 50 miles per hour. Then you see a red light and you hit the brakes. And you're very irresponsible. What did I say? Red line, red light. So you didn't really see the light. Um, so and you stop. Say that that's what happens. So let me draw some graphs. So the question is what do the graphs of position and acceleration look like? Position and velocity. Oh, I forgot to. Yeah, I forgot to put this in the poll, didn't I? Graphs of position velocity and acceleration. So I mean, if I would like to make you draw them because that's more fun than choosing options. All the time is positive. So something like this, something like this, something like this, um, something like this. Not the best drawings in the world, but probably, I mean, they're different from each other. So, what do I need to draw? Which ones did I cover already? So these are your options to choose from. Um, I don't know what other things to draw. Okay, this is what I'm gonna draw. I wanna edit my. Okay, so think about which is the graph of velocity, position, and acceleration. And I'm gonna ask you, what are you doing? Make the poll. Oh, now you're copying yourself sometimes. Right. So take a guess. So among these 6 graphs, one of them is closest to the graph of the position of this story. One is closest to the acceleration. One is closest to the velocity. Think about it. Have a vote. I think it's anonymous. If it's not, I don't care. We're all learning. Which ones are? Oh, hey, thank you. I forgot. A, B, C, D, E, F. All right, one person voted. Two people voted. I believe in you. Is there? There's no clock here. All right, I'm gonna give you 1 more minute because if you take a guess, I don't know. If you get it wrong, who cares? So, she's stopping now because the correct options are winning. And I like that. Uh, 5 seconds. 4, 3, 2, 1. Time up. Okay, so yeah, the correct option is 1. Look at that. Well done. So the position has to be this one. You at the beginning you've traveled 0 meters, and then you start traveling, and as you get faster, the velocity is going to increase. Maybe the position is the hardest one to guess. That means that the graph of the graph is going to increase. This is not a great drawing, but it's curving up. The slope, the velocity is bigger here than here, and then at some point you stop. So this graph becomes horizontal, stops moving. But the thing is, it never goes back. You never go in reverse, at least according to this story. It'd be really bad if you skip the stoplight and then went back. So that one's the velocity. That one's the position. The velocity, well, A and C are very similar. So if you said, I think both could be correct, honestly. So what is the velocity doing? So the velocity, you start out stopped. Here you have constant velocity. And so when the velocity is increasing, you're accelerating. When the velocity is decreasing, you're braking. And here you're stopped again. So that one's the velocity. This could be the velocity as well. Looks very similar. I didn't know how many. I couldn't think of more reasonable graphs to draw. And the acceleration was d, like you guessed correctly. So here, so when you're cruising, you're going at a constant speed. So here you have no acceleration. Here you accelerate, and then the velocity decreases. You brake, so the acceleration is negative because the velocity is decreasing. So that's what the acceleration looks like. Okay, so you did this really good. So you must really understand second derivatives. Good for you. All right, that's gonna be it for today. Tomorrow I'll talk for 2 seconds about third derivatives, and then maybe I won't talk at all. Just send you a YouTube video later. And then that's gonna be it.